you guys also have some homework for me today. So did that go better this time? A little bit? A little bit better? A lot better. A lot better. Slightly better. Okay. So did we still have a couple of issues that we need to resolve?
Yes.
All of 2.3?
All of 2.3? Okay, so induction is still giving us some trouble. All right, so let's maybe vote on one problem to talk about from 2.3 as a class.
Number 8.
All right, so any other candidates other than number 8? 4. Okay, so either 4 or 8.
And number 20.
And number 20 something?
From 2.2, number 20. That was
Okay, any other candidates for discussion? Yeah.
Number 10 from 2.2.
2.2, number 10. All right. Okay, so vote on one and only one. So the one that gave you the most trouble sleeping last night, maybe. It's the one that you want to vote for. All right, so all in favor of 2.2, number 10? Okay. All right, so 2. And 2.2, number 20? Okay, how about 2.3, number 4?
How many votes do we have?
You just have one vote.
Oh.
Only one. Okay, so let's start over really quickly.
I thought we were choosing one from each.
Yeah,
Nope, one total. If we have time at the end, we can talk about the other one. But for now, just one. All right, so 2.2, number 10, all in favor? Okay, and then 2.2, number 20? The 2.2 wasn't as bad, I guess, as the induction stuff. All right, so 2.3, number 4, all in favor? 4, okay, and then for number 8, all right, that's more than 4. So we'll talk about number 8. All right, so let's pull it up really quick. Ooh, yeah, this is a good one. I'm glad that you're wanting to look at this one. Okay, so we want to prove that the sum from I equals 1 to n of I times I factorial is equal to n plus 1 factorial minus 1 for n equals 1, 2, 3, on and on, forever and ever. Okay, so before we dive into this particular problem, let's review the basic parts of induction. So we said it's a simple, 3-step process? 3 easy steps. Step 1.
The base case.
Show the base case, yeah. And so generally that means you just pick the first value of n and verify that the formula works for that value of n. Step 2.
Induction hypothesis.
Inductive hypothesis. And so can someone elaborate on what that is?
What do you think the K is for? What the case value would be?
Okay, so something about the kth value, what you think that would be, but
1 to 2 would also.
You assume the case true and you prove k plus 1 is true.
right, okay, so the inductive hypothesis, we assume that the formula holds for the base case up through n equals k, right? So that's where that k comes in. So it's like we've established that this works for the first k many finite values. And so then step 3 is using that inductive hypothesis, we show that it also holds for the k plus first value, right? And so generally to get from step 2 to 3 is just algebra, right? Occasionally there's something a little trickier that comes into play, but usually it's just some algebraic manipulation and we just want to be clever about it or strategic about it or something. Okay, so in this case, we will do step 1. Base case is when n is equal to 1. So when n is equal to 1, notice that the sum just goes from I equals 1 to 1. So that just means that there's one term in that summation, right? And that's when I equals 1. So we would just have on the left-hand side, 1 times 1 factorial. 1 factorial is just 1, right? So 1 times 1 equals 1. Not too bad there. And then for the right-hand side, if we plug n equals 1 into our formula, we get 1 plus 1 factorial minus 1. So this gives us 2 factorial, which is defined to be 2 times 1, which is 2. So 2 minus 1 is also 1, so the left-hand side is equal to the right-hand side. So the formula holds, at least for that first value of n, that we think it should hold for. Okay, so then our inductive hypothesis in step 2 is we assume something, and in this case we assume, what does that look like?
N equals K.
Okay, so we assume that this should hold for n equals 1 up through k, right? So assume that we have the sum from I equals 1 to k of I times I factorial equals k plus 1 factorial minus 1. And then what I'm going to do is write what we want to show a little bit further down than I did last time. Because last time I wrote it right under this, but then I started working with this thing. So what I'm going to do is essentially get to my finishing line and then try to fill in the gaps in between. So what we ultimately want is to show that this thing also holds if we go up to k plus 1. Right, so we want to show that the sum from I equals 1 to k plus 1 of I times I factorial is equal to k plus 1 factorial minus 1. Right, so I've just swapped out everything that I saw as k here for k plus 1. So that k became a k plus 1, this k became a k plus 1. And then I still had the plus 1, the factorial, and the minus 1. Okay, so what questions do we have about the basic structure of this proof?
Wait,
Michael?
You just, oh, okay, I think, sorry, I first I got a little confused with where the extra plus 1 came from. I know you were just saying you had k plus 1 and then k plus 1, and it just clicked on me.
Great, yeah.
And that was also something that was giving me trouble on the other homeworks too.
Right, yeah, sometimes just swapping out the k and the k plus 1, it can be a little tricky when there's already a plus 1 in there, then sometimes it's easy to lose that. So if it helps, you can do some sort of circle or boxing so that you make sure and replace all of the circles here with the k plus 1s in what you want to show. Okay, so I'm interested in how many of you got to this point so far.
That's not a problem for me. It's
Great.
not
It's just, yeah, it's all that magic that happens,
Yeah.
right, between steps 2 and 3. All of that math magic. Okay, so for those of you who started doing some magic in here, what was your first thing that you tried? What was your instinct?
You can multiply by k plus 2. Because the factorials, if you multiply by k plus 2, it adds on, doesn't it? For k plus 1 factorial.
So if we multiply both sides by a k plus 2, is that what
You
you're?
have to, but yes. Oh, I'm just looking at the factorial in order to get the 2 in there. That's the only way I think of, but.
Okay, so right, so you kind of see that down here we could even get this into an easier to look at format, right? So I could write this whole thing as k plus 2 factorial, which is I think what you're, yeah, that's what you were seeing, and so you wanted to multiply by the k plus 2 to get it. But so what's a little bit tricky about just multiplying both sides by k plus 2, so that'll give us the k plus 2 factorial here, but then we'll have a minus k plus 2 term, and we kind of want to maintain that minus 1 in our formula. So So you can always try it and see if you can somehow manipulate that extra stuff to go over to the left-hand side. But I think there's maybe a more strategic way to do this. What else did you all try, Jake?
I manipulated the left side a little bit, pulled out the k+1 term.
Okay, so first of all, it sounds almost like we want to just remember what the summation looks like in order to work with the left-hand side a little bit. So, right, my first step might just be to write out what this thing looks like, and then also maybe what this thing looks like to see how to get in between those two things. So maybe I will do that in, we'll see how this pink is today. All right. What do we think? Is that visible?
Mhm.
Okay. All right, so like I said, this is just the sum of a bunch of different terms, right? So we start with I equals 1, plug it in, and then add to that what we get when we plug in I equals 2, so on and so forth, up through I equals k. So that'll look like 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial, all the way up through k times k factorial. And then down here, we should have the same thing, only with an extra term, where I is equal to k plus 1. Okay, so if we write that out, we'll get the 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial. We still have up through k times k factorial, but then we're adding on a k plus 1 times k plus 1 factorial.
That's what I did with mine when I started out, is that I started with the left-hand side of the one to show.
Mm-hmm.
And I know that k plus 1, the summation of k plus 1 and I equals 1 is summation of k to I equals 1 plus the k plus 1 times k plus 1 factorial.
Right, yeah. So I think what you're saying, Ruben, is you recognize that this thing has the inductive hypothesis part of it in it, right? Just plus this extra term that we needed for the final step.
Exactly. So what I did is I substituted that inductive hypothesis to the k plus 1 factorial minus 1 and try to work from there.
Okay, great. Yeah, so there are two different ways to proceed, and they're equivalent, right? So the way that you're wanting to go is you're going to start with this left-hand side and eventually try to show this right-hand side.
Exactly.
And so the left-hand side we've already written out as this pink stuff, and then we know that the first portion of this pink stuff we could substitute out with this right-hand side because of our inductive hypothesis. Ooh. Oh, you guys like that. All right. Cool. That's what we'll do then, since you're so excited about it. The other way to go, right, which like I said is completely equivalent, but it just sounds like it might be different, is to start with this and then just modify this to get what we want, right? And so that's how we've previously done this, is we would start here and say, okay, well, I just need this extra term added to make this left-hand side look like this one. So I'll just add that term to both sides of this equation, which should be valid, right? Because I can add the same quantity to both sides, and I'll be fine. And so then we would just manipulate the right-hand side to make it look like that right-hand side. But today we'll do it Ruben's way, which is slightly different, but again, completely equivalent. So you guys have seen the base case, right? You're fine with me erasing this? Okay, so I'm gonna switch from pink because I've decided that I don't like pink today. Are we fine with blue? I just feel like it's a little bit more readable. Some of you seem like upset that I'm moving away from pink. I'll get back to it, don't worry. Okay, so if we start again, yeah, with this thing. So I'm just gonna still write it in the summation so that we kind of remember where we are starting and then where we're gonna go. So we said we can write this as 1 times 1 factorial plus 2 times 2 factorial plus all of that stuff up through k times k factorial. And then we have that final term as k plus 1 times k plus 1 factorial. And like Ruben said, the first k terms in the sum, I already know something about, right? I can substitute in using my identity from the inductive hypothesis to say that this thing should be the same as k plus 1 factorial minus 1. And so to that, I'm just adding the k plus 1 times the k plus 1 factorial.
Could you factor out the k plus 1 factorial?
That sounds like a really good idea, right? So what you want to be a little bit careful about, right? So we see the 2k plus 1 factorials. In order to factor it out completely, we have this issue with this minus 1 that doesn't have that k plus 1 factorial. But we can circumvent that to some degree by just factoring out the k plus 1 factorial from this term and this term, and then leaving the minus 1 separate. And what's good about that is we want the minus 1 to be separate anyway, right? So you don't want to mess with that one too much. All right, leave it alone because it's supposed to stay kind of on its own for the end. Okay, so with that in mind, I'm first going to rewrite this in a slightly different order, just commuting some stuff, which I can do if I'm careful. All right, so I'm going to write this now as k plus 1 factorial plus k plus 1 times k plus 1 factorial, and then leave that minus 1 on the end the way that I want it. So all I've really done is just, moved this guy over. Again, I can do that.
Oh, there you go. Because once you factor it out now, then it works perfectly.
Then once you factor it out, it works perfectly. That's our magic that we needed. All right, so factoring out the k plus 1 factorial, what I'm left with when I factor it out of this term is 1. And when I factor it out of this term, k plus 1. And so I can combine this stuff together to get k plus 2. All right, so I've got k plus 1 factorial times k plus 2 minus 1. And this is what we want, but now you all are saying, wait, why is this what we want?
I thought it was it.
You thought, oh man, but it's so close. We are at the finish line, we just haven't realized it yet. We're still running.
This is pretty much where I got stuck.
That's k plus 2.
Because, that is k plus 2 factorial.
That is k plus 2 factorial.
That's
So it might help
Already over there.
if you write the k plus 2 in front of the k plus 1. It might make it a little bit more obvious. But if not, we'll still talk about why this is k plus 2 factorial. So yeah, it's just a general fact about factorials that, oh, I know, that n factorial is equal to n times n minus 1 factorial. And so the way to think about it is just this is the product of the first n integers, right? So if I just pull out the nth one, then I'm still left with the product of the first n minus 1 integers. So if it helps to think about an example, you could say, all right, well, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 5 times 4 factorial. And I mean, that should hold, right, regardless of what n is. Because you're just peeling off that last integer and then taking the product of the remaining ones. So once you see this, then you can rewrite the k plus 2 times k plus 1 factorial as just k plus 2 factorial. And then we still have that minus 1. So we look back over here, and yes, that is where we wanted to go. So at this point, step 3 is complete. So we can draw our little box or our QED or our cloud or whatever it is that we like to draw at the end of our proof.
Just shut myself down like the last.
That happens so often that we get to the end and then we're like, where do I go from here? And it's because you want to keep running, but you don't have to, and you just don't realize it. It's a weird analogy, but it works. Yeah, Jake.
So can we, I said, where you have in green, I said that equal to what we're trying to prove. So like that equation, we want that to equal k plus 2 factorial minus 1, and just make them look equal, because then the ones go away.
Okay, so yeah, I see what you're saying. That's a little tricky to do. And so the reason is, well, it's not tricky to do in general. It's tricky to leave your proof looking like that because you're essentially assuming what you want to show. And mathematically, that's a little, well, it's a little troublesome. Usually it works out fine, but there are certain times where if you assume what you want to show, then you find some true things, and so you feel like that then means that what you assumed was true, but that's not always the case. And so I'll give you an example in a minute. But what I would suggest is if you want to go that route, do that as sort of like your scratch work. So you would say, okay, is this thing equal to that thing? And for myself, I would always put like a question mark over it, just to remind myself that I'm not sure if these two things are equal, right? I'm trying to show that. And so then if you get down to the point where you have an identity, so I don't know, maybe you get to something like 1 = 1, and then you say, oh good, that works, so now I know that that's true. But then when you're writing up your proof formally, I would try to use all of the scratch work that you did in here to see how you can actually just get from this step to that step without necessarily setting them equal. So I hope that kind of makes sense,
Yeah, it does.
what I'm getting at. And yeah, this comes up a lot in proofs, and we haven't talked about this particular thing a ton yet just because we're relatively new to the proving things. But yeah, generally assuming what you want to show is tricky business. So an example that is, it's fairly silly, but I think it'll help illustrate why it's problematic, is just like in a real world context that's not math. So maybe I want to prove that I'm the smartest person in the world. Me. Like actually me, I'm the smartest person in the world. I want to prove that. So the thing is, it's not true. Okay, it's not true, right? But if I start out by saying, well, okay, let's suppose that I am the smartest person in the world. Well, if that's true, then I could probably get a position teaching mathematics at Sonoma State, right? And I would have survived up until this point because I'm really good at not, like running into traffic and that kind of thing. And there are a variety of other things that would be true about being the smartest person in the world that's also true about me, but that doesn't necessarily mean that that initial assumption was right. And so sort of like the best case scenario mathematically that you run into is you assume what you're trying to show, and then you do some algebra, and eventually you get back to the thing that you assumed, and you're like, oh, okay, cool, I showed it. But really you just like did some work and then undid the work to get back to what you started assuming. That's sort of like the best case scenario. And then the worst case is that you just confuse yourself terribly and you give up. So generally you do not want to start off by assuming what you want to show, and it's a cautionary tale. We all do it every once in a while, but don't. Moral of the story is try not to do it, and then when we ultimately do it, we'll be like, oh right, we weren't supposed to do that. Yeah.
Does that only apply for these inductions?
No, for any proof at all. All proofs. So there are some times when we assume things in proof, right? So for the implication statements, if then, we assume the if part, seek to show the then. That's fine, right? We don't assume that both are true. We just assume the first part and see if we get the second part. And then occasionally, right, we assume the opposite of what we want to show. And so that feels like, how is that really that different than assuming what we want to show? But remember, if we show the opposite of what we want to show and get to some sort of contradiction, so some fact that can never be true, then that means that initial assumption wasn't correct, right? So the opposite has to follow. Whereas if we assume what we want to show, we might get to something that's true, but it may not be like sort of the crux of what makes the statement true, is like the one true fact that you got to, maybe 1 = 1, which doesn't really have as much to do with the thing that you're trying to show as like a contradiction that can never be true. So that's at least the idea behind that distinction of assuming the negation versus assuming what the actual statement is. Yes?
Can you explain how you got from the first line to the second line?
This one to this one?
Yeah.
Okay. Yes, I will explain that. But I'd rather someone else explain it. So what do you all think? Can someone come up with a really concise way to explain how I moved from here to here? James.
She used her hypothesis at the top over here because that first k plus 1 factorial, she showed it in the pink over there is 1 times 1 factorial plus 2. And then we noticed that when we expanded the what we want to show portion, that we had like terms that were in the hypothesis also. So she just took the shorthand notation of the hypothesis and plugged it in instead of the expanded version of it.
Okay.
Yeah, so this pink bracket here is meant to indicate, oh, look, that matches up with this pink stuff. And so then we know that this pink stuff is equal to this expression. So yeah, I just substituted 1 for 1. Other questions or comments? Is this one a little bit less mystifying now? A little bit, and you know more about factorials now, which is cool. You know what I think is kind of interesting is a lot of people use this fact, but maybe not in this form. So what you all probably remember from like Calc 2 when you're doing the ratio test, which is where factorials often pop up a lot when you're first learning things. So you might have, had some ratio test with an n plus 1 factorial over n factorial, and you all got really good at saying, oh, this is just now n plus 1, right? Because the n factorials cancel. So you were really using this fact, you just didn't maybe like think about it in this form, right? Because really what you're doing now is just multiplying this thing over to get that. So it's cool when like things that you know relate back to things that you think you just learned, but it's really you knew that, you just haven't thought about it the right way.
It's been a while since we thought about it that way.
It's been a while. Yeah. So that's cool too, right? It's remembering things that are fun about factorials.
For summations, I
Yes.
don't really like too much about it. It feels confusing since we haven't been used to working with summations in a while.
Mm-hmm.
Most of the time it's always been like in algebraic form, but not in summation.
Yeah, so the summation stuff here for induction, it's almost just put in there to give you like an extra step to sort of throw you off. But really all you have to do is write out what the terms look like, and then it's just like one of those initial problems, right? But it's, yeah, maybe remembering how to do that can be a little bit tricky. So yeah, just generally with these summations, start at I equals whatever this lower bound is, plug that value in, that's your first term. Add to that what you get when you increment I by 1. So in this case that would be 2. Plug it in, add to that what you get when I equals 3, so on and so forth until you reach this upper bound. So once I is k plus 1, you plug that in, but that's where you stop. And then I don't know, did I put one on the homework with the product, the big pi notation? Okay,
No.
that's probably good that I I mean, those work similarly, except instead of adding all of the terms, you're just multiplying them, but that's even less familiar than the sigma. So maybe we'll do one of those for fun sometime. So like reviewing for the next exam, we'll do it, and then on the second exam, I won't put one of those, but it'll be a good way to review for it. Or maybe I will as an extra credit or something. Now you've been warned, now you know. Okay, so make sure your name is on those. I meant to bring a stapler today, and I forgot. But some of you all have been so nice to share your little staplers with each other. So try to get a staple in your paper. It's just nicer for our grader that way. You're less likely to lose track of your homework. So then just pass those towards the front. I will answer that question once I have all the homeworks in my hand.
Are you afraid of like
No, you're not why. Just I'm not good at multitasking, so right now I'm just like I'm collecting homework. That's what I'm doing.
I just like boycott turning in homework until we get an intelligence.
That's fine. If you guys don't want to turn in your homework, it doesn't really impact me that much.
I would have gone.
Thank you. Any others? You're just writing in the last thing.
I know.
Okay, so the question was about the midterm.
Yes.
That's right, because we took a midterm last week. Thank you.
Yeah,
Okay, so I'm trying something a little different this semester than I have in previous semesters with the midterm. And so I'm not sure how you all are going to take this news. You're not going to be happy, right? But so the thing is, you're probably not going to be happy regardless of what I say. Okay, so this is why I'm trying this thing this semester, is because previously people have told me, like, okay, when you say we're getting our midterms back, okay, if you give them at the start of class, then people are going to be, like, whatever, distracted, right, by the test and their grade. And maybe they'll be a little mopey, or maybe they'll be like, shh, I did so well, I don't have to listen. Something weird will happen, right, that affects you. But if I say, I've got them, but I'm giving them to you at the end of class, then all class are so nervous about it that you can't think through anything else. Okay, so this semester, at least for now, what I'm going to do is say, I have them for you, but you have to come to office hours to get them. What? What?
What if we have a class? That's only my midterm.
Okay, so there's some questions. The first question is, what if I have class during office hours?
Well, we have work during your office hours.
Or work, yeah. What if you have some other engagement? You really have to take a nap during my office hours today. That's understandable. And so in that case, I mean, I don't know. Worst case scenario, you either make an appointment or you just get it back from me Wednesday class. But I just don't want you all to be nervous during class time, and maybe you still are going to be because you're like, okay, later today I'll see it, and so I don't know. I'm trying it out. It's just an experiment. You guys can let me know how it goes, whether it's better than one of the alternatives. But I can say that generally the midterms were pretty good. And I don't say that unless it's true. So that's good. No, I don't lie about those things. So I think some of you have had me before, that I'll say something like, well, it wasn't the worst thing I've seen. But no, they were generally pretty good. So, yeah. So, right, I have office hours today at 3, tomorrow at 10. And then I guess, of course, we can do it in class on Thursday. But like I said, you can just drop by, see if I'm there, or send me an email to set up a time to grab it.
Bailey, will you be there after this class, or are you taking out somewhere?
I've got a meeting, so yeah, just try to do either office hours this afternoon or tomorrow, or email me, or set up a time right after class to do it, yeah.
Are the office hours today in your office or the math lab?
They're in my office, yeah. It's the Thursday ones that are in the math lab. Okay. Yeah, you guys. I knew you weren't going to be happy, but we're trying it out. We're going to see how it goes. Okay, so now that that's off of your mind completely, James.
Do you do the thing where you'll drop the lowest midterm if you get higher on the final?
Yes. Yeah, so that's a pretty standard math department thing. Not like universal, right? But most of us say, yeah, if one of your midterms is not so good, then as long as you do better on the final, then we'll replace the low midterm with a final. So that's right. Motivation to work hard towards the final.
What about the negation of that? Like, what if we did more of a
Yeah, it doesn't work the other way around, unfortunately. But I like the way that you asked that. It's very appropriate for what we're doing today. So with that in mind, I'll go ahead and pass out our handouts for today. So first we're looking at predicates and quantifiers. So this is just coming from your reading. We've already reviewed a little bit with that quiz. So we'll just do a couple of example exercises to further jog your memory, and then you can work on some more interesting stuff in group.
This stuff's not as bad as the.
Really? Yeah.
What? You guys want the worksheets actually?
Your end is different from the book. They had a squiggly end.
Yeah, the end of the book is more like a start end.
Yeah, I left like
No, like all right, so does everyone now have one? Anyone still
Looks like
need a
I
handout?
something we use in some
Does anybody want to take a picture of this before I erase it? It's so pretty. You can put it on your fridge.
Mom, what I do in school.
So like, can we set up a little before I have like a science thing I have to do? So, yeah, I want to work. So, fine. Does that work with you? I mean, come on.
All right, so everyone's a little worked up because of the midterm announcement. So let's take a minute to take a deep breath. Just relax. Right? We're here for another hour. Let's just be content with it. Find your zen. Get ready to talk about quantifiers.
Yay!
All right, so we're starting off with an example that asks you to find solution sets. All right, okay, you guys, what's going on? Roberto, what's going on? Okay, we're done with the bet. And then over here, we're talking about the N's and the Z's and stuff?
Yeah, I'm explaining the difference between the letters.
Okay. Okay, so let's talk about that as a group, right? Because we saw already in the book the N's and Z's are a little bit different. Maybe we don't even remember what those were. So in the book we had like this script N, which I'm using as what we call this sort of like bold N, even though it's not bold the way that we think about it, but it's like a math bold. So this is called what? What's the name for it? Natural numbers. And so what are some natural numbers?
0.
26.
Okay, so 26 is 1. I heard 1.
Non-negative integers.
Non-negative integers, right?
So it's not positive.
Is 0 included?
0 is included in our book. That's not standard. So by that I mean that there's it's not that this is an unusual thing to do, but the mathematical world is split about 50-50 as to whether the natural numbers include 0 or not. So since our book includes 0, we will. But just know that sometimes you might run across someone in the wild who would start the natural numbers at 1 instead of at 0.
Yeah, I did.
Then I'll write a little note reminding you that 0 is included.
That was so useful.
So actually when I learned about the natural numbers, I didn't include 0. So this has been a big shift for me as well, so I understand why you're having trouble with this. And you know, the way that natural numbers were defined to me was, well, they're called that because that's naturally how you count things. And so usually you start counting with 1. You don't usually start counting with 0.
Right. So you can also see all the non-negatives, so you just start with 1, you don't think 0 is negative.
Right, yeah, 0 is sort of a special case, but again, our book defines natural numbers to include 0, so we'll go with it. And so you can still think about these as counting numbers, but it's just allowing for the case that you don't have anything to count, I suppose. Okay, so then we also had this script Z, which I'm using as a math bold Z, and these are called the integers. So if I were to write the integers in set notation like this, how might I accomplish that?
-2, -1, 0, -1, 2.
Okay, and so it's only those 5?
With dots.
Dots.
Okay, dots on both sides, right. All right, so we've got this is called an ellipsis, right? Okay, -2, -1, 0, 1, 2, and then another ellipsis. So now we're saying that, yeah, there are infinitely many of these spanning from 0 in both directions, but these are just all whole numbers, positive, negative, or 0, where these are only the non-negative whole numbers. And then there was at least one other set that the book discussed that used a letter R, yeah. And this is right. All of the reals.
Does that include fractions?
It includes fractions. What else does it include? Okay, so yeah, rational numbers sort of includes fractions and some decimals, right? All fractions are rationals. The decimals that either truncate or repeat are considered rationals, but it'll also include all of those irrational numbers, which we can never write down,
So it's
unless it's like root 2, so I was kind of lying there.
So would be considered continuous then, from like -infinity to infinity?
Yeah, so right, writing it in set builder notation doesn't really make sense, but you might write something like interval notation, -infinity to infinity. So it's just any number that you can think about that doesn't have an imaginary component would be considered real. So that includes the whole numbers, it includes the rational numbers, and it includes irrational numbers, which would be stuff like pi or root 2 or decimals that never truncate or repeat. Like pi or e, 2 of our favorite irrational numbers.
Did you say you put non-imaginary numbers?
Right, so real numbers are a subset of the complex numbers, and they're the ones that have a 0 coefficient on I. So if they don't have an imaginary component, they're considered a real number. Don't worry too much about complex numbers in this class. They exist. We know they exist, right? We've come across them in other courses, but we're not really going to deal with them. So primarily we're looking with natural numbers, integers, and the real numbers. Although since it's come up, and it will probably arise again, so I actually don't know whether they use a cursive Q in the book or just like a hat-wearing Q, but the bold-faced Q is used to denote the rationals. And rational numbers are defined to be the set of all A over B, where B is non-zero, and otherwise A and B are both real numbers, or sorry, both integers. So just all ratios of integers where you're not dividing by 0, because we know that that's problematic. So I don't think that'll come up today, but it will arise in future sections in the book. So you might say, oh, okay, well, if Q is rationals, what are the irrationals? Usually we just use something like R minus Q to denote the irrationals, which seems weird because it's like we've got plenty of other letters, but that's just what we do. Okay, so then in the first example, we're finding solution sets for some statements given two different universes. So the first one, we're just going to work within the natural numbers, right? So all values of x in the natural numbers that satisfy the statement. So this first statement is 5x equal to 3. And now what I usually do, and you all might have been doing this on the homework too, is I just kind of solve these things like I'm working in the real numbers and then restrict it if I need to. So to solve this equation without any restrictions, we would do what? Just divide both sides by 5. So we get x equals 3/5, which is our solution in the real number system. But if our universe is n, then 3/5 doesn't live in that universe. So in this case, there would be no solution. But in the second universe, which is the real numbers, then we know the only solution is, yeah, the real number x equals 3/5. So you weren't asked about this, but we could talk about what solutions there are in the integers. So if I was in z instead, then what would my solution set be? No solutions, yeah. And then what about if I were working in the rationals? Would I have a solution there?
Yeah.
Yeah, and it would just be this 3/5. Okay, cool. And so, yeah.
How come, oh, I get it. So it's no solution for natural numbers because it's not a whole number, or why?
Yeah, exactly. So with our natural numbers, they had to be not only whole numbers, but non-negative whole numbers. But here we just fail at the fact that this isn't a whole number. So it doesn't live in that universe.
Okay.
And then in part B, we're asked to do the same thing, only solving 3x. Whoa, that's a different number that I meant to write down. 3x less than 7. So again, you might just solve this as you normally would. With inequalities, we can divide both sides by the same positive value without flipping the sign. If it's a negative value, then we flip. If it's 0, then we run away because bad things will happen. So dividing both sides by 3, we get x is less than 7/3. And so in our universe of the natural numbers, what does that solution set correspond to?
0, 1, 2.
Okay, so yeah, it looks like all of the non-negative integers that are less than 7/3 would be 0 and 1 and 2, right? Because this is, what, 2.3 repeating, something like that. And then how about if my universe is the set of all reals? Yeah, so it's just the set of all x, so that x is less than 7/3, and there are infinitely many of those, right? So if you like the interval notation, you could go from -infinity up to 7/3. Oh, and that would still remain open on the right-hand side. So 3 different values in our solution set for the natural numbers, infinitely many in the real numbers. Yeah.
So isn't it supposed to be that it's less than 2? Is it okay to include 2 in that?
Well, so this number is actually a little bit bigger than 2, right? It's 2.3 repeating, 2 1/3. So as long as we found natural numbers that are less than 2 1/3, then we're good. Yeah. Other questions? Mm-hmm.
So, compared to like part A and part B with if the universe is natural numbers, I don't exactly, I can kind of see, but not entirely see why A would be no solution and why we'd actually have a bit of a solution for B.
Yeah, so the main difference here is that in part A, we've got this equality, right? And since it's a linear equation, there's only one value that makes this true. And so it just so happens that the one value that makes it true is not a natural number, right? So if we're restricting our solutions to live in this universe, then we don't have any. Whereas here, we've solved for a range of values that satisfy this.
Right, I see, because you could actually have whole, okay. I see.
Yeah, because some of our whole numbers that we're allowed are less than 2 1/3, and it turns out that 3 of them are natural numbers. All right, so let's look now at some quantifiers. So this came up on the quiz. What is this one called?
Universal.
It's the universal quantifier. And so when we see this, how do we read it? For all. For all, or maybe even for any. And then this one is called existential. And how would we read this one? There is or there exists. So this one's called universal because it means everything in our universe is fair game, right? For all of the things in our universe. Whereas existential means there's at least one, right? So it could be that there's exactly one, there could be 2, there could be 10, there could be infinitely many. It could be true for everything, but all we know for sure is that there's one that it works for. Mm-hmm.
So could you also read it as there, like, for some?
Yeah, so for some, yep, there's at least one for some. Mm-hmm. That works too. Okay, so in example 2, we're working with the universe of the real numbers. And we want to determine whether the following statements are true or false, and these both involve quantifiers. So the first one is written as the universal quantifier x, and then the predicate x squared plus 2x minus 3 equals 0. So the way that we would read this really does just sound like for all x, and it's implied for all x in the universe, then this thing is true. For all x in the real numbers, this holds.
True.
Okay, so some of you say false, some of you say true. What's the reasoning behind?
Can you just do a counterexample?
Okay, so a counterexample would prove it false, right? So a counterexample would just be one instance of x in the real numbers that doesn't satisfy that equation. And so what's the counterexample that you find? Okay, so if we plug in x equals 0, then we get 0 plus 0 minus 3, which is a negative 3. That's not equal to 0, right? So yeah, because we have found one that doesn't satisfy this, that means that not all of them do, right? So our counterexample is x equals 0. There are probably many counterexamples, infinitely many as it turns out, because I think that has just the 2 roots, right? And they're both real. Okay, so then how about for part B? So in this case, we've got that there is at least one x in the universe such that the statement x squared plus 2x minus 3 equals 0 is true. I kind of gave this one away a minute ago, so if you're listening carefully. Okay, so you're saying it's true. She gave it away, it must be true. Why is it true?
Because there is a solution.
Okay, so there's a solution. Can you name a solution?
Plus 1.
Okay, so it looks like, right, if we factor this thing, we get a plus 3 minus 1. which then tells us that the true roots are 1 and -3. So either one of those would be the at least one that we need. In fact, we have exactly 2 solutions here, but we only needed the one for an existential quantifier. Cool. What questions do you have about just the distinction between the existential, universal?
So I'm guessing for like A has to go like, continuous, like you cannot break it off. Every X element must work with that equation.
Right, yeah. So with the universal, whatever the statement is has to hold for everything in your universe. So can we come up with an example that would work in the real numbers? So for all x, something that's true.
In the natural universe, all x is greater than -1.
Okay, so if we're working with q as the natural numbers, for all x, x is greater than -1 would be true. Can we think of one that works in the real numbers?
X is less than x squared.
Is that true?
Less than or equal to actually.
Less than or equal to? I'm not so sure if that works. X less than x squared? Yeah, so 0, and usually the fractions give you trouble with that.
Oh, that was good.
Yeah, like 1/2 is not less than 1, or yeah, it's not less than 1/4. But that's, I like the path that you're going down, right? We're trying to find things that are generally true.
X is 0 equals 1.
Okay, sure. Ooh, except 0 to the 0 gives us trouble there. Yeah.
X times 0
Chris?
0 to the 0. X minus 0.
Okay, so that one should work for all x. X minus x equals 0. Can't really argue with that. How about something like for all x, x squared is greater than or equal to 0? That should work too if we're in the reals, right? Yeah, so it's kind of fun to dream up some of these things as practice. So, tonight when there's nothing on TV, you've got some stuff to do. All right, so now let's look at number 3 where we're negating some of these statements. And so you guys probably remember from the reading that the negations, it kind of works like De Morgan's laws did, right? So you sort of like distribute the negation through. So let's see exactly what I mean by that. So the negation of a universal quantifier would be the existential. So to negate for all, you would say there is one. And then the negation of an existential is a universal. So those flip, but then otherwise you would also negate the statement. So in part A, for instance, if my original statement is for all x, there exists an m such that x squared is less than m. And I am working in the real numbers here. So like I said, I'm going to start off by just negating everything and then gradually distribute this through. So to distribute it to the universal, I said that turns into an existential. So I'll have there exists an x, and then I'm going to negate everything that's left over. So I'm just doing this step by step. And on your homework, you probably will just do it all at once, but just to see it, move it through one at a time. So I've negated this, and then I'm going to move to negating the existential here, which turns into the universal. Exists in x, so that for all m. And then I've got not x squared less than m. So how would I negate this statement? Okay, yeah. So this becomes, there exists an x such that for all m, x squared is greater than or equal to m. Okay, so in addition to negating this original statement, the way that we did step by step, we're also asked to evaluate whether the resulting statement is true or false in the universe. So, right, reading this again, it says there exists some real number so that for any other choice of real number, the square of our fixed real number is greater than or equal to the second real. Okay, so I see some people going and some are going So let's talk through this. What's your reasoning for either way?
And this infinity. There's no x, no other x can be. M could be.
Well, so remember that infinity isn't actually a number.
Well, it can be up to infinity. So any number you say for x, I'll just counter with a 1 greater than.
Okay, so Michael's saying, I can play this game with you where whatever x you claim works here, the at least one that you think you have, I'll just pick an m that doesn't make this true. Right, so even if I pick x to be like a billion, because I know a billion squared is going to be pretty big, you're just going to take a billion squared plus 1 or plus 0.1 or something. It doesn't matter, and that's your m, right? So there are at least some m's that don't work here for the x that I've picked. Well, what if I just picked a bad x? What if a billion wasn't the right one?
There is no x. There just isn't.
Okay. So essentially, it's based on the fact that there's no upper bound to the real numbers, right? So there's no x squared that's bigger than every other real number that exists, right? I can always go one step further, right, because they're infinite. So that's the idea behind this one. So this one is false. If you're ever unsure about that, you could always just go back to the original statement that we negated and see if that one seems like it holds water. So does it seem likely that for any x I give you, you can find at least one m so that m is larger than the x squared that I picked? So any x that I choose, you can find an m that's bigger than x squared.
So you would put like false and counter example and then use like 4 squared and then make m 17, something like that?
Well, so the tricky thing with saying that the statement is false is you can't necessarily just give a counterexample, because the counterexample would be for a specific x value that you picked, but I could have picked a different x value. So since we're saying that this one is like there's at least one that works, well, your counterexample may not have been the one that works if it does work. So generally here, we just explain why it's false. But we could also alternatively show that the negation of it is true. So for instance, any x that I give you, just choose m to be x squared plus 1, right? And then you're fine no matter what x I've given you. So for all of the x's that I can choose, you can find at least one m that satisfies this. Yeah.
So this is by, we end up proving the first statement by contradiction, right?
Proving the statement, you mean?
Yeah.
Sort of, except this one is actually harder to prove than this one is. So if we were going to prove the truth value of this statement, that would be easier than showing that this is false, because I can just say, all right, take any arbitrary x, choose m to be x squared plus 1, and then this is always satisfied. Whereas here, I'm very restricted to finding like the one x that would work if it does, and otherwise I have to show that any choice of x doesn't work.
So we just kind of reasoned through it, but we didn't prove it.
Right, yeah, so we could, we haven't proved anything we've talked through how we might prove this, which makes the negation of it false, and we can sort of reason through why this is false. But if we had to prove that this was false, it would be easier to prove that this is true. So yeah, it's the existential thing is nice in this case where we just need to find one value for which the statement is true, right? It's easy here. But if you're trying to prove something with an existential, it's actually trickier because you have to show that for any choice of that at least one, something either does or doesn't work, and that is not always so straightforward. So it has benefits and drawbacks for sure, the backwards E. Same thing for this one. Like over here, this is a little bit more problematic, whereas over here, it's a little bit easier to work with, and we'll see some more examples of why that is true. So let's also look at part B, and then you've got some to practice on your own. Kind of surprise for you. All right, so for part B, same thing. We first want to negate the statement, and then we want to determine whether that negated statement is true or false. So the statement as written says, there exists an x such that for all m, x squared is less than m. All right, so first thing we're going to do is negate it step by step. So I distribute the negation to the there exists, and that becomes right, so for all x, and then I've got negation of for all m, x squared is less than m. So when I negate the universal, it becomes existential. And then I need to negate x squared less than m. Yeah, so we did that right before. So flip it, add the equality part. So I get, for all x, there is an m such that x squared is greater than or equal to m. Okay, so questions on the negation. Now we need to think through whether the resulting statement is true or false. Okay, so for any x that I give you, could you find at least one real number that is less than or equal to the square of the number I gave you?
Yes. Yes.
Okay, so what if I give you x equals 3?
2.
Okay, that works, right? Because 2 is less than 9 squared. 3 squared, which is 9. How about if I give you something like x equals -5? So 0 works, yeah. In fact, 0 is going to be good no matter what x I give you, right? Yeah, because since we're working in the real numbers, this thing at smallest is going to be 0, right? So that m works for any x that I give you. So yeah, so this one is true. And in fact, you could choose m also to be any negative number, and that would be fine. Okay, so on the back side of that, you've got some similar examples to look at. Maddie is excited about the trig functions. So let's get in either 2s or 3s and talk through these. All right, so review your trig, and then on Thursday, we'll talk about 2.5. Good work today.
Is there going to be any homework?
I will post some homework on Moodle so you can get started on that. It'll be due next week.
I'm starting tonight.